Okay, so in the last video we talked about the concept of electric potential difference. This video will be a pretty short one, and then we'll finish up the unit. Okay, so the last main thing I want to talk about is the concept of the electron volt. An electron volt is a unit of energy, and we've seen it before, but now we're actually going to define it. So the SI unit for energy is the joule. But when you're dealing with the energy of individual charges, like electrons and atoms, the joule is a really large amount of energy. And you've probably seen before that the values for energy that we've been getting have had like really low negative exponents. And so the purpose of the electron volt is just to have a more convenient unit of energy, a smaller unit of energy that makes more sense in the context of talking about like atoms or molecules or stuff like that. And so that is what the purpose of the electron volt is. So the electron volt is written as EV for electron volt, and that is a unit of energy. And the definition of the electron volt is this. The electron volt is defined as the amount of energy it takes to move an elementary charge through a potential difference of 1 volt. Okay, and that's slightly different from what it says on the screen, so I'll say that one more time. 1 electron volt is defined as the energy it takes to move a charge of 1e, that is 1 times the elementary charge, through a potential difference of 1 volt. Okay, now, based off of how potential difference is defined, that amount of work would be equal to Q times delta V. And so just to repeat the definition for a third time, the amount of energy, the electron volt is defined as the amount of energy it takes to move a charge of 1e, okay, so 1.6 times 10 to the negative 19 coulomb, over a potential difference of 1 volt. Okay, that is how the electron volt is defined. So how much energy is that? Well, 1.6 times 10 to the negative 19 times 1 is very obviously 1.6 times 10 to the negative 19. And that is in joules. Okay, and so 1 electron volt is defined to be that amount of energy. Okay, so 1 electron volt, 1 EV by definition, is 1.6 times 10 to the negative 19 joules. And again, we've seen that value before. We commonly see electron volts or maybe mega electron volts in atomic and nuclear physics just because the energies involved are so small. But when you see an EV, just know it's a really small unit of energy, and you do need to understand how it's defined. Okay, so the energy it takes to move a charge of 1 E over a potential difference of 1 volt. Okay, keep in mind, this is not given to you in the data booklet. They do give you the elementary charge is 1.6 times 10 to the negative 19 coulomb, but you are expected to understand and know the definition of the electron volt and how it's defined so that you can come up with this conversion factor on your own. Okay, so this thing that I just put in a box here, that conversion factor is not given to you in the data booklet, so just keep that in mind. Okay, so just a few quick examples with that, and then we will be done with this unit. So let's say we have a proton, and it moves across a potential difference of 15 volts. And we are asked to calculate how much kinetic energy it gains in joules and electron volts. Okay, so we know that the potential difference is defined as the work done per unit charge. And so the work done on the proton is just going to be Q times delta V. But if it's a proton, we know that the Q is 1e, that's 1.6 times 10 to the negative 19 coulomb, times the potential difference of 15 volts. Okay, and if that's how much work is done on the proton, that's also equal to how much kinetic energy the proton gains because of the work energy theorem. And we talked about that in the last video. Remember that the concept of work is the energy gained, or I should say, the concept of work is energy added or removed from an object. Okay, so when we say that the amount of work done on the proton is 2.4 times 10 to the negative 18 joules, what we're really saying is that's how much energy was transferred to the proton. Okay, now work is not a type of energy. So when we say the proton gains that much energy, it has to gain it in a specific type of energy. And in this case, it gains it in kinetic energy. So how much kinetic energy does it gain? It gains 2.4 times 10 to the negative 18 joules. Okay, now we're asked to find the energy in joules and electron volt. There's a few different ways to do this. Okay, number one, we can just treat it as a basic unit conversion problem, as long as you know the conversion factor, and that conversion factor is that there is 1.6 times 10 to the negative 19 joules in 1 electron volt. And so if we just divide this number by 1.6 times 10 to the negative 19, we get 15 EV. Okay, the other way you could think of it is, well, I guess that's probably the the easiest way to think of it. Actually, it's just in terms of a unit conversion. All right. Notice, by the way, 15 EV sounds like way easier to say than 2.4 times 10 to the negative 19 joules, which is why we have electron volts to begin with. Now, if we're asked to calculate the speed of something, when we're dealing with speed, that means we're dealing with SI units. Okay, in that case, we have to use the energy in joules to get the speed to come out in meters per second. So just keep that in mind. Okay, so the speed of the proton after it's moved, we know that it has kinetic energy. We know kinetic energy is 1/2 mv squared. We know what the kinetic energy is now. And as long as you know the mass of the proton, which would be given to you in the data booklet, but here I'll just give it to you, negative 27 v squared. We can find v just using the magic of algebra, and I will just give you that answer momentarily. Okay, so I'm just typing this into my calculator. I get 5.4 times 10 to the 4 meters per second. Okay, so that is example 6. Okay, pretty basic calculation. I just kind of wanted you to see the electron volt calculation, okay, which again you can think of as a simple unit conversion. Okay, so pause there if you need to look at that some more. Okay, and then this example, I feel like we've already done this example. It says an electron is moved from point A having a potential of 25 volts to point B having a potential of 18 volts. What is the work done on the electron by the external force during the displacement? When it says by the external force, it's talking about the work done by the electric field. Okay, so let's put all this in context. Point A has a higher potential than point B. Okay, the electron has a negative charge. All right, if you consider those two things, number one, electric field always points from high potential to low potential, which means in this context, there's actually an electric field pointing from A to B. Okay, now, because the electron has a negative charge, in order to move the electron from A to B, we actually have to do a positive amount of work. Now, what I mean by that is that if the electron was, let's say it was a proton instead, protons feel a force in the direction of the electric field. Okay, so if you put a proton at point A, it's going to zip on over to point B just on its own. Okay, why? Because positive charge wants to go from a high potential to a low potential. Negative charge does the exact opposite. Okay, it's going to fight that. Okay, so in other words, the electron is not going to be attracted to point B because it has a lower potential. Okay, so in order to get it from A to B, we actually have to force it from A to B, aka we have to do a positive amount of work. Okay, now with that being said, the question says, what is the work done on the electron by the external force during the displacement? I think I misspoke before. Now that I think about it, because of what I just said, we have to force the electron from A to B. And so this has to be talking about the work done by our force, okay, the force that we have to apply, okay, because the electron is not going to move on its own from A to B, because a negative charge is not going to go down in potential just because. Okay, so the work from an outside force, we've seen before, is Q delta V. And so we know the charge of the electron is negative 1.6 times 10 to the negative 19 coulomb. And so the potential difference here, if we're going from 25 to 18, that is a potential difference of negative 7. Notice that the two negative signs are going to cancel out, and so we're actually going to get a value of approximately 1.12 times 10 to the negative 18 joules. And if you convert that to electron volts, you get about 7 electron volts. The other way to think of an electron volt, by the way, is if you just take it literally, electron volt. If we move an electron across a potential difference of 7 volts, that's 7 electron volts. Okay, and so you could treat it as a unit conversion and just divide this by 1.6 times 10 to the negative 19 coulomb. Or you can just say, okay, well, an electron moving across 7 volts, that's 7 electron volts of energy. Okay, you can just think of the unit electron volt literally. And that might save you a little bit of work. Okay, so pause it there if you need to look at this. Okay, and the FYI says since the electron is more attracted to A than B, we have stored this energy as potential energy. In other words, when I say that I have to do a positive amount of work on the electron, I'm forcing the electron from A to B. That electron now has gained electric potential energy. When I let the electron go, all the energy is going to zoom back out, and it's going to be gained by the electron in form of kinetic energy. Okay. So I'm going to go to the next slide. And so if I wanted to, I could calculate how much energy the electron has when it reaches point A again. It's obviously going to be the same amount. And so here, this question is actually saying if the electron is released from point B, what is its speed when it reaches point A? Well, they write this out in a really convoluted way. That they kind of use a conservation of energy approach. I would think of it more as a work energy theorem type of thing, where we know how much energy is going to gain in kinetic energy. We know that the initial kinetic energy is 0 if it's released from point B from rest, and so it's a simple matter of just plugging into the changing kinetic energy equation and solving for V. Okay. The way they write it out is not exactly the way I would have done it. I would have done it more along the lines of, net work is equal to change in kinetic energy, and we know what the net work is. It's Q delta V, and I would use VF squared, not I would use VF squared and VI squared and not V and U like they do here. But essentially, that type of calculation is just like the ones we've done before. Okay, so that's not really anything new. Now, by the way, if the electron is released from point B, when it reaches point A, of course, you could also say it's gained back 7 eV of energy, 7 electron volts of energy. Because again, if you have an electron and you move it across 7 volts, that is 7 electron volts of energy that's gained. Okay, but for the purposes of the speed calculation, the energy has to be in joules. Alrighty, so I think we will stop it there. Other than just to kind of mention kind of a random fact, but I always thought it's kind of an interesting fact. The electric field, along with the gravitational field, has a really interesting property where it has something called path independence. And basically what that means is if you have a charge and you move it from A to B, it takes some amount of work to do that, right? That's just Q delta V. We've seen that before. But interestingly enough, the amount of work it takes doesn't depend on the path that you take from A to B. Okay, so in other words, if I take my positive 15 microcoulomb charge, if I move it from A to B along this path, or I move it in a straight line, or I take some roundabout path, the amount of work done is still the same no matter what the path is. Okay, and that's because the electric force is what's called a conservative force. Okay, so the work is independent of the path because the electric force is a conservative force. I don't know that you'll ever see that word, conservative force, but in case you do, a conservative force is basically a force in which the work done in moving an object is independent of the path you take, okay, regardless of what that path is. Okay, so kind of a random fact, but just in case it ever comes up, I wanted you to have seen that term before. And gravity also has the same type of property, because gravity is also a conservative force. Okay, the analogy with gravity is let's say, if I take a ball out of my pocket, if I lift it straight up into the air, it gains a certain amount of potential energy. If I take it out of my pocket and I wave it around for 20 minutes, and then I lift it up 1 meter, it still has gained the same amount of potential energy. Okay, so regardless of how I got it there, if it goes 1 meter higher than it started, it gains a certain amount of potential energy. Okay, no matter how it actually ends up getting there. Okay, so gravity also is a conservative force. Alrighty, so I think we will stop it there. We are basically done with this unit. I would highly encourage you to finish all of the problems on your worksheet to prepare for the test on Friday. As always, please let me know if you have any questions, and I will see you guys in the next video.